theorem is the set of natural number is a countable set. Now when a set is said to be a countable set, if there is one-to-one correspondence between the set of natural numbers. So if F is a mapping from N to the set A, this set A is countable if there is one-to-one correspondence between the set of natural numbers and A, right? Or in other words, we can also say that if this F function is 1, 1 and on 2, then we say that A is countable, right? Because we need to show that N is a countable set, then we have to define a function from N to, instead of A, I must write here N, right? Because I need to show that this is a countable set, right? So we have to define a mapping from N to N for this. Define phi to be a mapping from N to N. And let me define this mapping by phi of N equal to N for all N belonging to the natural numbers. Now I need to prove here the three things for N to be a countable set. First one is phi is well defined, and then I show that phi is 1, 1 and on 2, right? Okay. When a function is said to be a well-defined function, a function f from x to y is well-defined if x1 equal to x2 implies f of x1 equal to f of x2. If I consider two elements to be equal, then I have to show that f of x1 is equal to f of x2. Then the function is said to be well-defined function. Please don't confuse this definition with the definition of a 1, 1 function. When a function is said to be a 1, 1 function, let me also recall this. For a 1, 1 function, we take two different points, which implies f of x1 is not equal to f of x2. That means if different points of x have different images in y, right? This is the first definition. This definition can also be written in another way, that f of x1 equal to f of x2 implies x1 equal to x2. That is, f takes different values at different points. This is the definition for the function to be a 1, 1 function. You have to start from two different points and then get f of x1 not equal to f of x2, or if f of x1 equal to f of x2, that implies x1 equal to x2. But in case of well-defined, we take two equal points. Please remember these two important definitions. Now for a function to be a well-defined function, let's take m equal to n, right? Two equal points. I have to show that here the function is f, here the function is phi. So I have to show that phi of m is equal to phi of n, right? But by this definition, what is n? It is phi n. So can I write for n phi n? Similarly for m, I can write phi of m, because this is for all n belonging to the natural numbers, right? So it is itself proved as a well-defined function. So therefore phi is well-defined. Then secondly, 1, 1. When the function is said to be a 1, 1 function, for this we have to consider, let me consider the second definition, that phi of m is equal to phi of n. This should implies that m is equal to n. But again, by the definition, what is phi of m? It is m. And what is phi of n? It is n. So therefore, phi is 1, 1. Easy? Alright. Third is onto. If f is a function from x to y, when this function is said to be an onto function, if every element of y has at least one pre-image in x. If every element of y has at least one pre-image in x, or we can also say that if for every y belonging to capital Y, there exists at least one x belonging to this x, such that f of x is equal to y. This is the definition for the onto function, right? So here for onto function, we have to consider here this is your x and this is your y. We have to take one element from this natural number, the set of natural number, and for that element there should exist at least one pre-image in x, but here x and y both are n, right? So let n belongs to the natural numbers, then by definition phi n is equal to n. Phi n is equal to n. F of x equal to y means y that is belonging to y has its pre-image x in x, right? So phi n equal to n means here we have taken n from the set of the natural numbers, right? That is phi is from n to n. So how can we say this? This n which is belonging to the set of the natural numbers, this having its pre-image n in, again that n belonging to the set of natural numbers, right? This shows that phi is onto. So phi n equal to n is showing what? It is showing that n belonging to the capital N has its pre-image n in capital N under phi. So therefore phi is onto. Now since phi from n to n is 1, 1 and onto, therefore this n is a countable set. This is what the definition of the countable set is. If phi is a mapping from n to the given set, then phi should be 1, 1 and onto, right? Or there is a one-to-one correspondence between n and that set, given set. So phi is defined on n to n, and we have proved that phi is 1, 1 and onto. So therefore n is a countable set.